Okay, so good afternoon to one and all. So I am very glad to inform you that today you are having the guest lecture on the topic of photonics and its future applications. So today we have Dr. Sanjay Kumar Govre sir with us. So welcome sir. So due to this hybrid mode, we have to adjust somewhat. So, sir is working as a professor and dean academics at BKIT Bhalki. So, sir has pursued his PhD in electronics and communication department from IIT Kharagpur in 2013, and his PhD topic is design of all glass photonic crystal geometry for telecommunication and sensor applications. Sir has completed his MTech with fiber optics and light wave engineering in May 2006 from IIT Kharagpur. So both the degrees sir has pursued from IITs, and currently sir is, as I told, sir is working as a professor and dean academics at BKIT Bhalki. So he is having the teaching experience from 1919. So around 25 years teaching experience sir is having. So the awards, if you see, so a research grant of rupees 20 lakh for VGST Bangalore for a period of 2 years on design of photonics and communication system. Research grant of rupees 10 lakh from VTU Belgaum for period of 3 years on photonics devices for optical networks. Award of IEEE ICIIS 2007 grant, and that is from Peradeniya University, Kandy, Sri Lanka, with registration grant of USD 220. Award of rupees around 10,000 per month scholarship for pursuing PhD at IIT Kharagpur. So this is the basic things which shows sir's work in this photonic field. So actually sir's resume is very large. It is difficult for me, but still I can summarize as in this field, the person is known from the paper publications and his contribution in the research. So, to summarize sir's paper publication, so sir is having the Google Scholar 60 citations, Scopus 38 citations, and H index is 4, and Web of Science citations are 22, and H index it is 4. So sir is around having around more than 50 paper publications, 3 sponsored projects. 2 students have completed their PhD under sir's guidance, and as 4 awards mainly sir has received. So he has attended more than 30 STTPs, FDPs, 2 books sir has written, 1 patent has been published, and around 30 guest lectures and expert talks have been delivered by sir. So I am really thankful sir for accepting the invitation and being available for us and our students. So without wasting much time, I request sir to proceed with the lecture. Okay. Sir, you just please, just 1 minute. Just this you need to operate. You be seated here. Okay, online, am I, the voice is audible properly? Screen
Yes,
is
ma'am.
visible? Okay.
Yes, ma'am.
Okay. So sir will take the charge. Please, sir.
Okay. Good morning to all. This is new to me, right? बैठ के बोलना थोड़ा मुश्किल रहेगा. Okay. 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 Keeping aside my biodata, right? Let us move to the topic, right? Advances in photonics. Okay. Whether you heard this word, कभी पहले सुने हैं? Photonics. Okay. Prerequisites to photonics is what? Optical fiber communication. Whether you have studied optical fiber? Optical fiber?
Yes, sir. Yes.
Okay.
Yes.
Okay. So what is optical fiber and what is its use? What is optical fiber and what may be the use of optical fiber? Audible, na? Okay. This semester you are studying optical fiber. Okay. How many modules are completed? Units, modules. Right. So if you look at the fiber, right, broadly we can say that there are two types of fibers. Right.
So
Single mode fiber and multi-mode fiber. There are two types of fiber. Right. Multi-mode fiber has got its own disadvantages. Right. So it is not used for long distance communication, whereas we prefer the single mode fiber. Correct. But whatever the single mode fiber we are using, it has got its inherent disadvantages, and we don't have any solution for that. Whatever fiber we are using today for long distance communication has got some inherent disadvantages, जिसका कोई इलाज नहीं है. Or you can say that whatever the performance we are getting from single mode fiber is what has reached the maximum limit. So to solve those problems, we need to go for one more type of fiber known as what? Photonics, right? So for using photonics, you can design a fiber, you can design the devices, like you can design the gates also, right? AND gate, OR gate, NOR gate. You can design full adder, half adder. You can design flip-flops. You can design memory using flip-flops, right? So it has got a vast area wherein photonics has got the applications, or you can use these photonics for the sensing applications also, right? So in one word, we can say that photonics can be used for any applications. Okay. So with this brief, right? So this is brief about the photonics lab, what we have at our college, and these are the members working in the field of photonics, right? And these are the few softwares we have available with our lab for designing the photonic crystals. Okay. So what I'll do is I'll start with brief introduction, right? And then we'll go to the motivation, right? What motivated us to go for a new type of fiber. Okay. Right. If you look at this, right, you know better than us, right? What this figure says? In 1 minute, right? In 1 minute, these are all the activities are taking place in the year 2021. Now we are in 2022. So obviously these data have increased, right? So you can see that, right? There are 21.1 million text sent. There are YouTube 500 hours of content uploaded, right? Right. You can see that there is a Tinder, there is a Insta, there is a TikTok, right? That means in 1 minute, this much amount of data is being generated today, right? Now you might be having question that what way this is related to photonics, correct? We are talking about photonics, but we are talking about what? The amount of data being generated in one minute. Now you can visualize how much amount of data being generated in 1 day when we are talking about for only 1 minute, right? So in next slide, I will explain what is the use of this data, or what is the relation between this data and then the photonics, right? Okay, this you might have seen, or you might have heard this law. Sune hai,
Yes.
Moore's law?
Yes.
Right. Now, if you look at this, right, year, right, from 1900 to 2025, right? Now we know that, right? Electronics started with what? Electronics started with what? Tubes. Then we have transistors, right? Then we have IC, right? So if you look at this, now you look at this, right? There is a compact desktop. There is a Pentium series of computers, right? Pentium 1, Pentium 2, Pentium 3. Probably you might have not heard about these, right? Now, what system we have today? Any system configuration? System, desktop or laptop? What is the configuration you are using? How many of you have laptop? कितने लोगों के पास है? What is the configuration you are using? That is the software configuration, whether it is dual core, core duo, Core i3, Core i5, Core i7,
Core i5.
Core i5, right? Okay. So now if you look at this Pentium series processors, right? Probably you studied 8086 microprocessor, you have studied 8051 microcontroller, you have studied it, right? So we are talking about what one processor. We are talking about one processor. Now at the end of the day, what we want is we want the processor to be very speed. Whatever task is there, that should be completed in a less amount of time, right? So how you can achieve that? One is what? You have a processor with that capability. The other one is increase the frequency, right? So everything we have done it. We have increased the frequency, but there exists a limitation. So after that, what we do is instead of using one processor, use the two processors, right? Instead of two, use the four processor, quad processor. Probably if you look at your mobile, which has a, how many processors you have? जो आपके पास मोबाइल है, how many processor it has got? Octa processors.
Octa-core.
Can okay, whether voice is audible, online students? Hello? Voice is audible? Hello?
Yes,
Okay, due to
audible and visible both.
yes, due to electricity problem, there was disturbance. Okay, so
चाहिए कैमरा
नहीं वो ऑडियो नहीं होता ना
कैमरा ओनली कैमरा इस प्रकार से हाँ हाँ साउंड right. So if you look at this slide, right, whatever I have discussed, it is there on this slide, right. The thing which is marked in red is the important one, right. What is the first line says? We're talking about optical computing. We're talking about optical computing because the speed is 3 into 10 to the power of 8 meter per second, right. So that is the major advantage of going for the optical. Second important one is what the optical storage, right. Presently we don't have a optical storage facility, but using this we can design a optical memory, right. Second one, what it says is light does not have the time response limitations, whereas electronics has got that disadvantage. So this is second motivation. Third motivation is what? Efficiency and speed of computers, as well as significant shrinking in their size and cost. So I'm talking about the VLSI chip, right? So these are again the advantages of optical, or you can say photonics, right? These are all what the advantages. But if you look at the last line, what it says, ये सभी तो बहुत अच्छे हैं, right? We are getting everything, but lastly what we are saying, building an optical computer will not be easy. Whether this is disadvantage, whether this is disadvantage, no, this is a challenge. He is not saying that not possible, is what, not easy. और लाइफ में इजी कुछ नहीं मिलेगा, इजी मिलेगा अप टू बी 8th सेमेस्टर, बी एक बार खत्म हो गया, कुछ इजी नहीं मिलने वाला, राइट. अभी सभी पेरेंट्स हैं, so up to your education it is everything is easy. After your education but there is a limitation, right? So what I do is I will use less amount of time. Doesn't go up to bomb. So what is this? How much what happens if you assume that this amount of power is wrong? As result progresses, it reduces. Signal strength reduces. Right. Right. So what we'll do? Let us assume that from this place to say up to 100 kilometer it will go. After 100 kilometer, the signal strength vanishes. What is the solution for that? Repeaters. Right. What is repeaters then? What is repeater and amplifier? Whether both are same or they are different? Amplifiers and repeaters. Both are same. Right. We know what is amplifier. What is amplifier? Increase the signal strength. Right. So after 100 kilometers, signal strength is reducing. Use the amplifier. It increases. Now what is repeater then? Repeater is what basically it is a receiver, amplifier and transmitter. Right. That means repeater consists amplifier. So we need a repeater. Right. What repeater consists of? Receiver, amplifier and transmitter. That means the cost of repeater is very more because it has got both receiver as well as transmitter. So let us assume that from this place to Bombay, say we require 10 repeaters, then cost will be more. Right. If you want to reduce the cost, number of repeaters should be minimized. If you want to minimize the number of repeaters, you have to pump the more power. So यहीं पे घूम रहे हैं. So that is the limitation of what? Single mode fiber. इसका कोई solution नहीं है. Then second one is what? About the dispersion, right? Someone is saying about the loss, right? Loss is something different from the dispersion, right? Okay, there is one more term comes into optical fiber known as non-linearities, right? That means keeping the fiber core area 12 micron. I want to pump the more power. I'll keep 12 micron only. I'll pump the more power. That may be the solution. But if you do that, it will get into non-linearities. What is non-linearity? What there are few parameters comes into picture known as what? Cross phase modulation, four-way mixing. Right. Probably you will be studying that in third or fourth or fifth units. Right. So these are the non-linearities, and that we don't want. Right. And then it crosses the dispersion. Right. Dispersion basically gets into the crosstalk. Right. So if you look at this pulse, right, let us assume that this is the pulse we have pumped into the optical fiber. Right. After covering some distance, its shape is changed to this. What has happened here? If you look at this pulse, transmitted pulse, and then this pulse, what is the change? Strength is decreased, width is increased. Right. Now for this we have a solution. What is the solution we have? Signal strength is reduced. Use the amplifier. Signal strength बढ़ जाएगा. But what is the solution for this? Or what happens if there is a dispersion? क्या होगा इससे क्या होगा? What is this? What may be the problem? You have a answer here, right? We have launched two pulse, right? 1, 0, 1. For 1 we have a pulse. For 0 nothing. For 1 again we have a pulse, right? So and there is a dispersion. So you can see that what is happening here due to dispersion. If you look at this area, what is happening? There is an interference, right? Interference of one pulse with another pulse. And this leads to what? Crosstalk. This leads to what? Crosstalk. Followed this? This is one of the problem in single mode fiber, right? But what is the phenomena by which there is a dispersion? Why this is happening? Why there is a pulse width increasing? Okay, I'll show you this. Right. The reason for the dispersion. Right. If you look at the left hand side, right, how many cars are there? There are 8 cars, right? And they are starting at the same time. There is a race and they are starting at the same time. And then what is happening on the right hand side? Whether all the cars are running at the same speed? No. Right. Some car may run at 60, 70, 80, 90, 100. And at the destination, what happens? All the cars will reach at a different time. Right. So if you consider that is a pulse at the starting point, that there is a time period there. But at the receiving end, it is increased because we'll be measuring from first car to last car. So this is the phenomena by which there is a dispersion. Because light consists of different wavelengths, and different wavelengths will travel at different speed. Right. So this is the cause for dispersion. Right. So limited by the mode area, we have discussed single mode. There is a bending loss. Right. जब भी fiber bend होगा, there is associated losses are there, and also cannot be made large for compact non-linear devices. And then coming to the one more limitation. One limitation is what? Core area. You cannot increase beyond 12. Second is what? If you look at this is known as what? A dispersion. Right. Dispersion consists of two important things. One is material dispersion, and it is inherent. Whatever material we are using for fabricating fiber, silica, uska wo fixed rahega. So this curve is what? For material dispersion, and this is for waveguide dispersion. When we say waveguide, it is core and cladding, right? So combining this, we known as a dispersion, and at 1.3 micron or 1300 nanometer, we have a zero dispersion. Followed this? Combinedly, material dispersion plus waveguide dispersion will give you dispersion, and that gives zero dispersion at 1300 nanometer. What is the meaning of this? Zero dispersion at 1300. That means if you use at 1300 nanometer, there is no dispersion. Whatever problem we said, that will not be there, right? But what is the window we use for communication? Which window you use for communication? 1550. We use 1550. At 1300, there is a zero dispersion. You might be having doubt that use 1300. Why you want to use 1550? But at 1300, losses are more. If you look at this curve, at 1300, we have a more loss than 1550. So there are two things. One is dispersion, the other one is loss. 1300 पे dispersion zero है, but loss is more. At 1550, loss is less, dispersion is more. Which one is used? 1300 or 1550? कौन सा use करेंगे? Because at both sides we have some advantages and some disadvantages, right? So we use 1550. That means loss is also an important parameter, right? Presently we have a 0.2 dB per kilometer loss in fiber, and that can be compensated by using amplifiers, right? So 1550 we will use for the long distance communication, right? Now disadvantage is what? We can shift this 1300 zero dispersion hai, you can shift this to any value above 1.3. You can design a fiber in such a way that zero dispersion can be shifted to 1.4, 1.5, 1.6, any value you can shift it. So for that reason, at 1550, loss is less, and we can shift that zero dispersion from 1.3 to any value. For that reason, we'll use 1550. Now drawback is what? Is it possible to shift from 1.3 to 1.2, 1.1? That is not possible in single mode fiber, because there are some applications wherein 800, 900 nanometer window is also used. At that point, we have a minus dispersion. And in case of single mode fiber, it is not possible to shift below 1.3. Above 1.3, you can shift anywhere. So what are the two drawbacks? Core area and then the dispersion. So these are the two important motivations for going to what? Which topic we are discussing? Photonics. Okay, so these are the two important things. One is endlessly single mode. Second one is the tunable dispersion. Now what is endlessly single mode is what? Even though if I increase the core area from 12 to 20 to 30 to 40, it should be in a single mode only. That is known as what? Endless and single mode. And using single mode fiber, it is not possible. But using photonics, it is possible. Okay. You might have studied this equation, right? V is equal to 2 pi r by lambda square root of n core minus n cladding square. If its value is pi, right, then it is known as what? Single mode fiber. If it increases, then it becomes multi-mode, right? So that equation can be little bit modified in photonic crystal fiber so that we can adjust the value of V, right? This we have studied, right? Now, this is what the motivation for getting into photonic crystal. Now, what is photonic crystal? Right, up to until now we have discussed why photonic crystal. Now, what is photonic crystal? Right. If you're looking at this figure, what is photonic crystal? There is a variation in the refractive index, either in one direction, two direction, or three direction. Then it is known as that 1D, 2D, 3D photonic crystals. Right. This is a brief history. Right. I will not get into that. Right. So you can look at this. This is what? Variation in is only one direction. This is two direction, and this is three direction. Now, out of these three, predominantly 2D is used. 1D is very, what you can say, is not used. 3D is very difficult to fabricate, even though it has got many advantages, but it is very, very difficult to fabricate. So most of the research is there in the two-dimensional photonic crystal fiber. Right. If you look at the semiconductor, right, there exists a gap between valence band and conduction band. Right. Similarly, there exists a photonic band gap in photonic crystal. Right. Now, what is the significance of this photonic band gap? If you look at this figure, right, this is known as what? A yellow color is known as what? A photonic band gap. What is the meaning of that photonic band gap? Right. The meaning of photonic band gap is what? Whatever the wavelength we are getting, this wavelength, right, from 0.4 to say 0.5, right, we'll design a photonic crystal in such a way that only the wavelength falling under that is allowed to propagate it. Outside that is blocked. Outside that is blocked. जो wavelength को वो pass कर रहा है, that we can use as a fiber for communication. यहाँ से transmit कर रहे हैं and we are receiving at the other end. It is known as what? Photonic crystal fiber. और जहाँ पे block कर रहे हैं, जो wavelength is blocked, that concept can be used for memory. What is memory? I have some data which I need to store it, right? So using this structure, what is happening? That wavelength is blocked there only. So that is used as what? Memory. Right. These are the applications of few applications of photonic crystals. Right. What are those? One is photonic crystal fiber. Then you can design some active and passive devices. Right. Then you can go for integrated optics. We can design a sensors using photonic crystals. That means area of photonic crystal is vast. You can use it anywhere. Now, if you're looking at this, right, this is the input, right, and it is propagating on both the directions. Right. I'll show some results here. Right. Now coming to photonic crystal fiber, right? We're talking about single mode fiber has got disadvantages, right? So there are two things. One is photonic crystal fiber. The other one is photonic band gap fiber. This is known as what? A photonic crystal fiber, and this is photonic band gap fiber. Now from this figure, what you can say? What you are observing from these figures? This center area is known as what? Core. Known as what? Core. And for communication, using fiber, we require two things: core and then cladding. And then light will propagate by a mechanism known as what? कैसे travel होगा? Total internal reflection, right? So same phenomenon is used here also. So center part is what? Where there is no air hole is used as core, and this other part is known as what? Cladding. In cladding, we have air holes. So center part acts as core. This whole part acts as a cladding. And what is the rule for total internal reflection? Refractive index of core is less than or more than cladding? कौन सा? If you look at refractive index of core and cladding, what is the relation? किसका ज्यादा रहना चाहिए? कोर का ज्यादा रहना चाहिए क्लैडिंग का for total internal reflection to take place? कौन सा? There are one is the angle of incidence, जहाँ पे आप इंसिडेंस करेंगे Snell's law, and with respect to दोनों का अगर सेम रहे तो क्या होगा? If refractive index of both core and cladding is same, whether there is a TIR? No. ये इक्वेशन देके तो बोलो. Look at this. Look at this. Which refractive index is more? Core का या cladding का? अच्छा यहाँ पे अब now this is what silica. जो background है is a silica, right? Refractive index of silica is कितना है? Okay. And this part is cladding. Cladding में there is a silica and there is a air hole. Air का refractive index कितना है? 1. Right. So effective refractive index of cladding is obviously less than the core, and there is a total internal reflection. And this is known as what? Photonic band gap fiber. What is the difference between those two figures? और दोनों same है. What is the difference? Now here there is no air hole, but here there is a air hole in the center also, but size is more than air holes in the cladding, right? Now the photonic band gap advantage is what? As the light is propagating in the air, there is no loss. There is no loss. But again the drawback of these are what? There are many advantages. Disadvantage is what? Difficult to fabricate these type of fibers. जहाँ पे if you look at this, there are n number of air holes in the cladding. जब हम fabricate करेंगे, what will happen? That is the disadvantage, right? So this I'll skip. This is the disadvantage of fiber. क्या हो रहा है इसमें? If you look at this, the air holes have got a different size, right? And यहाँ पे there is a difference, right? जो last row में है, right? There is a change in that shape, or two air holes may combine with each other. These are the drawbacks of what? Photonic crystal fiber. Whether still we want to go for it, we have got two advantages. One is endlessly single mode, the other one is tunable dispersion. Two advantages. Disadvantage is what? Fabrication. Disadvantage is what? Fabrication. Whether still we want to go for it or we want to skip here. जब fabricate करना ही नहीं होगा तो फायदा क्या है, right? But drawback is what? There is a solution for this also. What is the problem here? Air hole deformation. Air hole deformation, right? And solution for this is what? Replace the air holes with rods. Air hole का refractive index कितना है? 1 है. Choose some material with a refractive index of say 1.01. 1.01, right? So वहाँ पे अभी rod है. There is a rod there, and there is no question of air hole deformation. Correct? That means whatever the disadvantage we had with a photonic crystal fiber, air hole crystonic fiber, we have proposed a new type of fiber wherein instead of air holes, use some material with a little bit refractive index, which is more than 1. Right? Now we have a various parameters here. In single mode fiber, we have only two parameters: refractive index of core, refractive index of cladding. Only two things. Now here you can see that apart from that, we have a lattice pitch. The distance between two air holes is known as what? Lattice pitch. You can vary that, you will get a beautiful results. Then air hole diameter. जो air hole है या जो rod है उसका diameter या ratio of d by pitch, या कोई हम वहाँ पे doping concentration डाल रहे हैं. So we have got various parameters and we can play with them and we can design a fiber, right? So this we have proposed and we have published this in Optic journal, right? So now you can see that this is what V parameter of PCF with respect to pitch by lambda, and we have varied D by pitch from 0.4, 0.5, 0.6, 0.7, 0.8. So this is a roll PCF. This is our proposed PCF, all glass photonic crystal fiber. So you can see that for 0.4, 0.5, the cutoff value is pi 3.145. So if you draw a line from 3.14 line, right? So this 0.4 and 0.5, both these values, for both these values, your fiber is in a single mode, and you can increase the diameter from 12 to 36. 12 to 36. 3 times we can increase the fiber core area. What is the advantage? From 12 to 36, you can pump more power. If you pump more power, number of repeaters required will be minimized, and then overall cost will be less. You design anything, right? End of the day, what they will ask? You want to purchase a mobile, right? You went to a mobile phone store and you looked into 10 different types of mobiles. Lastly, कौन सा लेंगे? We want everything, right? Processor चाहिए, RAM चाहिए, camera चाहिए, right? Selfie camera चाहिए. We want everything. We want everything. But finally, there is a phone which has got everything and cost is 80,000. लेंगे? Probably out of 100, 1 or 2 may get it. Rest, they finalize on what? Cost, right? Similarly here also, right? You design a communication system, but its cost is more, right? Nobody will listen to you, right? They will say very good, but they say that cost is more. So if you increase core area from 12 to 36 micron, that means roughly you can pump 2 times more power into the fiber. So you can reduce the number of repeaters required. And also what we have done is we have changed the doping concentration. जहाँ पे हम rod डाले हैं, right? We have changed the doping concentration of that from 1.8 to 13.5. That has also shown a very good result, and we can use this for the communication purpose. Right? This I have discussed, right? Medium dispersion, waveguide dispersion. Right. There is a one more dispersion known as what? Chromatic dispersion. This is there in single mode fiber. There is a modal dispersion in multi-mode fiber that we are not discussing. In single mode fiber also there exists a chromatic dispersion. I said that combination of material dispersion and waveguide dispersion. Dispersion is there in single mode fiber also, and it accumulates over the length of a fiber or a length of a distance. Right? यहाँ पे pure pulse है. जैसे आप ट्रैवल करेंगे 10 किलोमीटर 20 50 100 किलोमीटर, the chromatic dispersion accumulates. When it accumulates, this what happens? There is a widening of a pulse. And how many the rate at which we are operating today, we are talking about how many bits transmission in 1 second. How many bits we are transmitting? 1 bit, 2 bit, 8 bit, 10 bit, 100 bits, 1000 bits. कितना bit हम transmit कर रहे हैं? If you look at internet speed, कितना रह गए? 1 Mbps, 10 Mbps, 100 Mbps, or 1 Gbps. If you look at 100 Mbps, what is the meaning of 100 Mbps? 100 into M is what? 10 to the power of mega is what? 10 to the power of 6. 100 into 10 to the power of 6 bits in these many bits we are transmitting. And if there is a dispersion, what will happen? All the pulse will collide with each other, and there is a crosstalk. Right? So there is a chromatic dispersion which is there in single mode fiber also, and there must be a solution for this. Right? Let us assume that over a length of 100 kilometer, right? Unit of dispersion is picosecond per nanometer kilometer. Right? So let us assume that after 100 kilometer, right, the accumulated dispersion is what? Say 100 picosecond. Over a length of 100 kilometer, the accumulated dispersion is how much? 100 picosecond per nanometer kilometer. and we need to compensate that. We need to compensate that. So for that purpose, we need to design a dispersion compensation fiber, known as what? Dispersion compensation fiber. अगर 100 picosecond generate हो रहा है, you design a fiber in such a way that it generates minus 100 picosecond, minus 100 picosecond for using a small length of fiber. So plus 100 and minus 100, what will happen? They will cancel with each other. जैसे 100 किलोमीटर तक एक फाइबर है, and at that point of time 100 picosecond generate हुआ, use a small, say 1 meter 2 meter of fiber which generates minus 100 picosecond. So you connect there, plus 100 minus 100 will get cancel each other, and now we have a fresh pulse, right? So that is known as what? A dispersion compensation fiber. And you can see that कितना तक आ रही है? minus 600 तक we are able to generate, minus 600 picosecond per nanometer per kilometer. So you can use this fiber for compensating the dispersion which is accumulated over a length of a fiber. And there are some applications wherein which frequency, which wavelength we are using? 1550. We are using 1550, right? But we are not only using 1550. We are using a window. We are using a window, and at 1550 we have a less dispersion. Above 1550, below 1550 we have a dispersion. But we need to design a fiber wherein we have a flattened dispersion over a bit. If you look at this, right? So from 1.3 to 1.7, kitna dispersion hai? How much it is? Minus 0.5, minus 1.5. From 1.3 to 1.7 wavelength, 1.3 to 1.7, we have a dispersion of minus 1 to 0.5, which is very negligible. Right. Hope you are following this. समझ में आ रहा नहीं आ रहा? Probably what we think is, right? Probably मैं जब student था मैं यही सोचा होगा. We are studying optical fiber. Why we need photonic crystal fiber, right? Most of you might be having this doubt. But end of the day, right? As I said, once you complete your degree, people will ask such questions like, which branch you are? Electronics, and they will ask this question, why you have chosen electronics and telecommunication? जब लिए तो हमको पता नहीं था हम क्यों लिए बोलते, क्यों लिए था आप लोग? Why you have chosen ENTC? Any specific reason? हमको कंप्यूटर करना था, सीट नहीं मिले इसलिए ETC करें? No. Very few might be having that, right? I want to do ENTC, but most of us will do just for that, right? हमको कुछ ये नहीं रहेगा. But you'll get this question first. या कोई कंपनी में आप एप्लीकेशन डालें, वहां पे वो क्वेश्चन ही पूछेंगे, why you want to work with us? Reason is what? Reason is what? Salary. But ये हम उसको बोल नहीं सकेंगे salary बोल के, but we'll say other words. Your company is very good, it looks after employees, right? Similarly, the topics are also right. You know single mode fiber, they know, right? Once you complete your degree, electronics and communication, they will ask you question on optical fiber, right? But if you know more than that is what photonic crystal fiber, right? You can add on that, right? So along with single mode fiber, sir, I know something about photonics also. That gives you an added advantage, right? Right. Last also we have loss also we have compared with all the fibers, and our proposed glass has got 0.4 dB of loss, which is a little bit more than the existing fibers, but still the work is going on in order to reduce those loss. Because if you look at this 2.7 to 0.44, 0.35 is what the single mode fiber. At 0.35 is older value. Now we have 0.2 dB per kilometer. Per kilometer loss is 0.2, right? Right. This is about what the fiber application, right? We want to design a fiber using photonic crystals. One of the application we can go for what the designing of a sensors, or more particular biosensors. Biosensor is what? For using what? Biosensors meaning is for health related, right? You can check sugar level, you can detect the cancers, you can detect the COVID, right? One of my student is working on this, right? I'll get into the result only, right? Design parameters for photonic sensor, and he designed this for detecting the cancer, right? Right. This I'll skip. Right. These are the parameters which basically comes into the sensor. Right. One is full width at half maximum, the quality factor, the sensitivity, right? Detection limit, figure of merit, right? So this is the paper he got accepted and published in IEEE Sensor Journal, right? So what he has done is, right, this is what a two-dimensional photonic crystal. It is 18 cross 7. There are 18 cross 7 holes are there, right? And it has got a two photonic band gaps, right? In the earlier figure I shown only one band gap. Here we have two band gaps, right? So what he has done is, here he has removed the sum of the air holes, right? So that acts as a waveguide. By removing the air holes, if you look at this figure, so what he has done is 1, 2, 3, 4, 5, 6, 7, 8 air holes he has removed it. Moment you remove it, it acts as a waveguide. Waveguide means what? Light will be traveled through this. And if you remove only one air hole, then it acts as a resonator. So you can see that this is the waveguide. You can say from this side we'll give the input. This is another waveguide. At this will be looking at the values, output waveguide. And in the center he has removed one air hole. That acts as a resonator. That is known as what? Point defect, right? So you can see this figure, right? The base is silicon dioxide. Again, all these are can be fabricated using VLSI technology. Okay. This is the experimental setup. So this is the sample wherein we are keeping this designed photonic crystal. Right. There is an optical source. Right. For optical source, as you know, we can use either LED or laser. And for detector, we can use photo detector, pin, or there is one more. APD, pin, and photo detector. Avalanche of photo detector, pin, and then the photo detector. Okay. So optical source we have used. Some light will be coming through this. Right. There is a polarization. When it comes to this sample, right, I'll show you the results, right? So these are the results we'll get it, right? So these are the refractive index of normal cell and then the cancerous cell, right? The basal cell has got a refractive index of 1.36. Normal cell, if it is infected with cancer, refractive index will be 1.38. For breast cell, it is 1.385, 1.399, and cervical cell 1.368 and 1.392. So you can see that there is a variation in the refractive index for normal cell and for the cancerous cell. Okay. Right. Okay. Now you can see that we are giving the input, right, from one end. Now you can see that there is a sample here, right? We are getting some intensity at the wavelength, operating wavelength, and this curve is for what? Normal cell, right? If that cell is infected with cancer, there will be a shift in the wavelength. So you can see here, right? One is this blue is what? The normal cell, and red is the cancer cell. What is happened here? One is there is a wavelength shift and there is an increase in the intensity also. So if the cell is infected with cancer, it will show the change in the wavelength. So by looking at that, we can say that there is a detection of what? Cancer, and we can take the precautionary measures. Right. All these figures are with respect to different cells, different types of cancers. And we have done extensive research on this, right? We have changed the radius of the air holes, right? You can see that, right? 84.8, 95.4, 106, right? So we have changed the radius in order to get the best result. So you can see that on this side, right? There is a wavelength shift, there is a full width half maximum, quality factor, sensitivity, detection limit, and figure of merit. So by changing the value of radius, we have measured these parameters, and we can conclude that you can see that there are some values which are shown in red. Right? You can see that there is a 768.5. What is that? Sensitivity, right? And then there is a shift in the wavelength is 211.19. Then sensitivity is 15,085. Figure of merit is 159. Here sensitivity is 6024. And we can say that for a RC value of 106, we are getting the very best result. Also, we have changed the lattice constant also, right? The distance between the two air holes, right? And from this, you can see that there are few values which are shown in the red. Right. And we have compared our work with the others' work also. You can see that the sensitivity is 330, 720, 2214. But in our proposed work, we got sensitivity of 15,085, a marked improvement. And then also the size. The size plays a very important role in electronics. We want everything, but size should be very small, right? If you look at the evolution of TV, computers, or mobiles, right? We have many more things in the mobile, but that size is very small. So here also you can see that the size is only 48 square micrometer, right? So wherein the size is very, very small. So this is about what brief about the photonics. For undergraduate students, I don't think this will be helpful. If you want to pursue your MTech or further PhD, right? This will be very good area for your research. Even if you do for MTech, there are simulation tools are there which are available with us. You can contact madam or you can contact me, right? I'll provide those softwares for you if you want to do some sort of research in the area of photonics. Any project can be done using simulation or hardware record. Yeah, the trend is, I don't know what is here, but in our college, trend is what? For doing project, giving to somebody else. Okay, right? But please keep in mind that once you complete everything, as I said earlier, up to your 8th semester, everything is okay. After degree होने के बाद, you will get maximum questions from what project you order. If you want to do job, the job करना है, मतलब बैठे तो जब नहीं, maximum questions you get from project. Maximum questions you will get from projects and from the, whether you have studied basic electronics. You say 70% of questions you will get from these two. The problem is basic electronics you studied in first sem, by 8th sem you will forget everything. And next is important project that we have outsourced to somebody else, right? In the Viva, we can manage it because you are our student. हम क्या भी सोच के पास कर देते हैं या मार्क दे देते हैं. But the person who is giving you job, he needs some knowledge from you. लेट अस अज्यूम दैट कोई एक प्रोजेक्ट का नाम बोलो आपका जो सीनियर करे होंगे, एंड मोस्ट ऑफ द टाइम यू विल फॉलो योर सीनियर्स, राइट, फॉर गुड थिंग एज वेल एज फॉर बैड थिंग. विथ रेस्पेक्ट टू प्रोजेक्ट, फॉलोइंग योर सीनियर इज वेरी बैड थिंग. किसी से करवाए होंगे, राइट, से आजकल एक चल रहा है IoT, XYZ using IoT, home automation, office automation using IoT. Next, you can do using microcontroller, Arduino. That Arduino comes under IoT only, right? Some sort of project using the microcontrollers, right? Either it is 8051 or Arduino or some other thing, right? Whatever project you do, my suggestion is try to do by yourself. बिकॉज यूर अंडर ग्रेजुएट स्टूडेंट्स, आप कौन सा करेंगे इंपॉर्टेंट नहीं है, आप खुद करना इंपॉर्टेंट. मोस्ट ऑफ द टाइम यू डोंट नो हाउ टू डिजाइन ए पावर सप्लाई, 5 volt पावर सप्लाई डिजाइन. हाउ मेनी ऑफ विल बी एबल टू डू इट? प्रोबब्ली कोई भी नहीं. वी हैव स्टडीड दिस, राइट. देयर आर 3 टाइप्स ऑफ रेक्टिफायर्स: हाफ वेव, फुल वेव और ब्रिज. विच वन इज बेस्ट? व्हाई? Answer is correct, but why is best? Efficiency of bridge is how much? 81.2. Ripple is 0.48. Same thing is there for full wave also. Then why to go for bridge? Now these are the questions you'll be getting in the jobs. और हम भूल गए. If you are able to do it, if you are able to do it with yourself, you will be studying that. Which book you have referred for basic electronics? Right. We have forgotten it. Right. Probably हम आजकल क्या है, everything will get in mobile. So book हम शायद देख ही नहीं रहे हैं. But I suggest you purchase a VK Mehta book for basic electronics. और until your degree completion or until you get job, daily 4 पेज उसमें पढ़ना, VK Mehta, where you'll get all the knowledges. Right. Bridge is best because center tap transformer is not required. Right. Otherwise we need a center tap transformer. Right. So what you do is, madam, आप ये कर सकते हैं, सिंपल पावर सप्लाई भी करा सकते हैं. बिकॉज व्हाट आई डू विथ माय स्टूडेंट इज आई विल नॉट अलाउड टू गो एनीवेयर. लैब में करेंगे, अगर रिजल्ट नहीं भी आते तो ठीक है, कोई प्रॉब्लम नहीं. राइट. यू डिजाइन ए 5 volt पावर सप्लाई, दैट इज द बेसिक रिक्वायर्ड फॉर एनी प्रोजेक्ट. आप कौन सा भी करो, 5 volt सप्लाई चाहिए. राइट. हम क्या करेंगे, जब प्रोजेक्ट आएगा जो करके दिया है, इन द एग्जामिनेशन विल एक्सप्लेन इट्स ऑपरेशन. सर यहाँ से इनपुट है, ये एलसीडी है, यहाँ रिजल्ट आ रहा है, बट वी डोंट नो हाउ टू डिजाइन ए पावर सप्लाई. एंड advantage what you have is you get every answer in YouTube. You stuck up somewhere, right? You'll get n number of videos in YouTube. For example, how to design a 5 volt power supply. YouTube में आपको n number of videos will get it. उसको सुनो, try to do it in lab, because that gives you the what, the practical knowledge will give you the more courage. Theoretical क्या होगा, हम पढ़ेंगे, एग्जाम देंगे, भूल जाएंगे. So whatever project they may do, but try to do it with yourself. अगर possible नहीं है, कहीं कहीं शायद facility नहीं रहेंगे, in that scenario also you need to look into each block. अगर माइक्रो कंट्रोलर यूज कर रहे हैं, कौन सा माइक्रो कंट्रोलर यूज कर रहे हैं? 8051 इज द बेसिक माइक्रो कंट्रोलर. जब हम बाहर से कराएंगे तो ही विल गिव सम अदर माइक्रो कंट्रोलर, उसका जरूरत ही नहीं रहेगा, बिकॉज ही वांट्स टू टेक मनी फ्रॉम यू. अगर छोटा 8051 माइक्रो कंट्रोलर लगाएगा, व्हाट इज द कॉस्ट ऑफ 8051 माइक्रो कंट्रोलर? 250-300 में मिलेगा. एंड दे विल चार्ज हाउ मच? 10 to 12,000, आई सपोज 10, 12, 16,000 पर प्रोजेक्ट, जिसमें एक माइक्रो कंट्रोलर रहेगा, एक एलसीडी रहेगा, एक जिगबी रहेगा, इन मोस्ट ऑफ द केसेस. You can purchase those things and you can do in your lab. Time is there.
Video by making that video of I want to take this picture. You just Okay, meanwhile, if you want to ask any question or you want to give any feedback, you can. Yes.
This question is any national or international projects are going on in the field of photon. In India, there are few universities where this work is going on. That too only simulation. We don't have any facility for experimental. There are some universities in India that do it. In India, it is only the simulation.
Anybody from this side? Online students, if you have any question, you can type in the chat box or you can ask. I will convey your question to sir.
Best strategy is you should have two questions for every topic. By every class, for every class, every class, they rectify. But this you should have why. And why you rectify and what is rectify. That's the topic question you need to change it. That's what I'm telling you. Then it is what? Two-way learning. As far as me, the difference between me and you is what? That difference is very rough. कोई एक टॉपिक है ये उल्टा पहले पता रहता है एक क्लास आना है तो पढ़ के दूसरा पहले आऊंगा ये घंटे के बाद आपको बता दैट इज द क्या अगर क्वेश्चन नहीं पूछते हैं तो टीचर बोलेंगे बिकॉज़ वी डोंट नो दैट और इसी डोंट नो आपने क्या करते हैं तो क्या There's a question like how it is helpful in the health sector. As I said, this work what we have done is basically used for prevention of cancer. Now, currently we have worked on detection of the tumors. But now, from last 2 years, we are observing is 10 to the power of milli का कितना है milli 10 to the power of minus 6 minus 6 उसके बाद that means this is factor of factor में natural factor of class है within factor of set we calculate about it so it positive or negative but as said that this Photonics can be used for memory because optical memory we don't have we have electronic memory So the problem is going to look at the optical communication scenario. The medium of communication is like in fiber. Right. Now, moment it comes to the repeaters, right? What we need to do, we need to convert that optical into electrical, amplify it, reconvert that to light and then transmit. That means even though we have a capacity to transmit data in EBPS, that is for figure, due to the repeaters, it is not possible. Now, how to use it as a memory? Band diagram. What I said is that band diagram significance is what? If the light follows within that band gap, that is telling that 1200 to 1400 ka band gap. If your light is within the 1200 to 1400, it will travel. Below 1200, above 1400, it is not allowed to propagate. अंदर जाएगा वहीं पे that concept can be used as a so light is gone into the structure so वहाँ नहीं है that can be used as a
Screenshot I have. Now I will make it.
no problem.
You can discuss on that. Okay, if everyone is having it down.
This slide with you. There is something on email.com. Yes, if you have any doubts, you can wait.
Okay. So thank you, sir, for such wonderful session. So actually, not only basics of the new trend in optical fiber, that is photonics, but along with that, whatever applications you have discussed, definitely that will create interest in the students for some their project work and all that things. And I will definitely contact you, sir, if we need any help. And we look forward for your future cooperation. Okay, I'm thankful to sir from our department, from Sweri management, as well as from our student side. Okay, thank you. Okay, you can leave the session. So just a minute. I will come.